Welcome to this concept explainer, brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today we're taking a deep dive into a really foundational concept, magnetic force from our unit, moving charges, and magnetism. And our mission, as always, is to make this simple, clear, and absolutely exam-safe for you. So, let's start with something you might have seen in pictures. The beautiful auroras, the northern lights. They're caused by charged particles streaming from the sun. But have you ever wondered, why don't those particles just hit the Earth everywhere? Why did they curve around and spiral down only at the poles?
That is a very interesting question. It must be something in the Earth's environment that's deflecting them. Perhaps our magnetic field.
Exactly.
Yeah.
And here is where it gets really surprising. If you take an electron and place it in a very, very strong magnetic field, if that electron is stationary, nothing happens. Zero force.
Nothing at all.
Nothing. But the very instant that same electron starts moving, it feels a strong force.
Wait, what? So the field only cares about the motion of the charge, not the charge itself. That's so different from an electric field.
Precisely. And that's the core idea today. The magnetic force is basically a force that only acts on moving charges. At the most fundamental level, think of the magnetic force as a sideways push. It's the push or pull that a magnetic field, we call it the B field, exerts, but only on a moving charged particle. If it's not moving, there's no force. To really get this, let's use an analogy. Imagine you're riding a bicycle, okay, going perfectly straight.
Okay.
And someone runs up and gives you a push, but exactly from the side, perpendicular to your path. What happens?
Well, I won't speed up
Yeah.
or slow down because the push isn't from the front or back, but my path will curve. My direction will change.
Exactly. Your speed remains the same, but your direction changes. That sideways push that only causes deflection. That is the essence of magnetic force. And, this force must exist because experimentally we see things like electron beams curving in a magnetic field without losing any kinetic energy.
Oh, I see. So for that to happen, the force must always be perpendicular to the velocity.
Precisely. Now let's build a mental image for your exam. Picture a magnetic field, the B field, as millions of invisible arrows all pointing straight into the page you're looking at.
Okay, arrows pointing in.
Now, a stream of blue charged particles enters from the left, moving horizontally. That's our velocity v. As soon as they enter the field, they start to curve in a perfect circular arc.
Why a circle?
Because the field applies a force, F, that is always perpendicular to their velocity v. And it's also perpendicular to the field B. This constant sideways push is what forces them into a circle. The path curves, but the pace, the speed, is constant. Now, let's connect this picture to the formal Ensert definition. When both electric and magnetic fields are present, we have what is called the Lorentz force. Could you please read out that equation for us?
Of course. It says, the force on an electric charge Q due to both of them can be written as F equals Q into E plus V cross B, which is equal to F electric plus F magnetic.
Thank you. So that full equation is the Lorentz force. The first part, Q times E, is a simple electric force. We're focused on the second part, that magnetic force term. F equals Q times V cross B. That cross product is everything. Let's break it down into a few simple steps. Step 1. The force F is proportional to the charge Q and the speed V. More charge, more speed, more force. Step 2. The force is also proportional to the magnetic field strength. B, a stronger magnet, gives a stronger push. Again, very intuitive. Now, step 3 is the critical one, the geometry. That cross product, V cross B, means the force is always perpendicular to both the velocity V and the magnetic field B. This gives us the magnitude of the force. F equals QVB sine theta, where theta is the angle between V and B.
Ah, so that sine theta term is the key. If the charge is moving parallel to the magnetic field, then theta is 0, sine of 0 is 0, and the force is 0. And if it moves perpendicular, theta is 90, sine of 90 is 1, and the force is maximum, right?
You've got it. Absolutely correct. And that leads us to the most beautiful and often misunderstood part. Step 4. Because the force is always perpendicular to the velocity, the magnetic force does zero work on the particle.
Wait, that's a bit confusing. If a force is acting and the path is changing, how can it do zero work? Isn't work force times displacement?
It is. But work is F times D times cos of the angle between them. Here, the force is always perpendicular to the displacement, which is along the velocity.
So the angle is always 90 degrees.
Yeah.
And cos of 90 is 0.
Exactly. The work done is always 0. The force changes the direction of the velocity, but it cannot change its magnitude, which is the speed. So the kinetic energy, half mv squared, remains constant. And when you have a constant force that's always perpendicular to velocity, what does that remind you of?
Centripetal force from circular motion.
Perfect. The magnetic force acts as the centripetal force, so we can set them equal. QVB equals mv squared by r. And from this, we can find the radius of the circular path. R equals mv divided by qb. This is a crucial formula. We'll just do a quick example. Imagine a proton moving perpendicular to a B field of 0.1 Tesla at a speed of 3 times 10 to the power 6 meters per second. If you plug in the mass and charge of a proton into our radius formula, r equals mv by qb, the radius of its circular path comes out to be about 31.4 centimeters.
So just about a foot. That's a very predictable path.
It is incredibly predictable. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com. Now, very quickly, let's connect this idea of a force on one particle to something bigger. A current in a wire is just, well, billions of charges moving together.
It's a collective flow.
So if we sum up the tiny Q times V cross B force on all the moving charges inside a conductor, what do we get?
You would get the total force on the wire itself, the macroscopic force.
Exactly. And that gives us the famous formula for the force on a current carrying wire. F equals I times L cross B. This is the direct link. It's the principle behind every electric motor, and it all starts with that simple sideways push on a single electron. Okay, now let's tackle 3 silent killers. Common misconceptions that cause students to lose marks. Wrong idea number 1. Students often assume the magnetic force speeds up or slows down a charge, just like an electric force does.
Why do they think that? Is it just because force generally causes acceleration?
Yes, they see F and think F equals ma, so speed must change. But the correct idea, as we discussed, is that magnetic force only deflects. It never changes speed. Just remember this phrase. Magnetic force equals perpetual perpendicular push. It curves the path, but the speed is constant. Wrong idea number 2. Confusing the directions. Many students think the force F points in the same direction as the magnetic field B.
But we just established that they are perpendicular.
Right. The force F is always perpendicular to the field B. Remember, F, V, and B form a right-handed triplet. If velocity is along the x-axis and B is along the y-axis, the force has to be along the z-axis.
Oh, okay. So if I just remembered that the field and the force are perpendicular, I won't lose marks on the direction.
You will not. And finally, wrong idea 3. A stronger magnetic field always means a stronger force.
But that's not true because of the angle.
Exactly. The angle matters most. If the particle moves parallel to the field, sine theta is 0 and the force is 0. Doesn't matter if the field is 100 Tesla strong, no force. Remember, perpendicular gives force, parallel gives 0. All right, to lock this all in, let's go over our memory anchors. First, the phrase to repeat in your head. Force is always perpendicular. This makes the path curve without changing speed. Next, the physical gesture. The right-hand rule. Everyone hold your right hand flat. Point your fingers in the direction of velocity, V, B, E, day. Now curl your fingers towards the direction of the magnetic field, B. Your thumb automatically points in the direction of the force, F.
And if it's a negative charge, like an electron?
Simple. You just reverse the direction of your thumb. It's an incredibly useful tool for solving problems. And for an extreme association, just think of an astronaut pushing off a wall in the space station.
Yeah.
That's their velocity, V. If a powerful external magnet, B, pushes them from the side, they won't fly straight. They'll just spiral in a circle at a constant speed, trap. So to summarize our deep dive on magnetic force in 3 quick exam-safe bullets. Bullet 1, the magnetic force on the moving charge is F equals Q times V cross B. This cross product means the force is always perpendicular to both velocity and the magnetic field. Bullet 2, because the force is perpendicular to motion, it does 0 work. This means the particle speed and kinetic energy remain constant and only its direction changes, often in a circular path. And bullet 3, the unit of magnetic field strength is the Tesla, T. 1 Tesla is the field that puts 1 Newton of force on 1 coulomb of charge moving at 1 meter per second perpendicular to the field. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is PROF Sam, right?
Yes, ProfSam.com. Study hard and all the best.